In this video lecture, I will discuss rotational kinematics and the quantities that describe the rotational motion of objects. I'm going to limit the discussion to rotation of rigid objects. The rotation will happen about a fixed axis of rotation, such as, for example, this figure skater. The axis of rotation will pass through their geometric center, and so as they enter this rotational motion, all points of the figure skater's body will rotate about this fixed axis of rotation. In the context of rotational motion, it is convenient to measure the displacement during rotation in terms of angles of rotation. The angle through which the object rotates is called the angular displacement. So let's look at this example. This compact disc rotates in counterclockwise direction about a fixed axis of rotation. I can assign a reference line which is perpendicular to the axis of rotation, and I can measure the angle through which a radial line from the CD rotates over time. So if this radial line does not overlap with the reference line, then it is at some angle, theta 0, from the reference line. And then after some time, the radial line will be at a different angle, theta, from the reference line. The difference between the two angle readings, theta minus theta 0, will be the angular displacement, delta theta. This definition of angular displacement is very similar to the definition we had for linear displacement, which stated simply that the linear displacement is equal to the final position minus the initial position. So you can see how there is a parallel between the two concepts, and we will see that later that there will be more parallels between linear and rotational kinematic quantities. The definition of angular displacement states that when a rigid body rotates about a fixed axis, the angular displacement is the angle swept out by a line passing through any point on the body and intersecting the axis of rotation perpendicularly. By convention, the angular displacement is positive if it's counterclockwise and negative if it is clockwise. The convention for the direction is extremely important. So when the rotation of the object is in counterclockwise direction, the angular displacement is positive. When the rotation of the object is in clockwise direction, then the angular displacement will be considered negative. The units for angular displacement in the metric system are the radian. Let's see how the radian is defined. Again, here is our CD that rotates in counterclockwise direction. If I consider a point on the edge of this CD, after rotating through an angle theta, this point will have traveled a distance that is equal to the length of arc S on the edge of the CD. And if the radius of the CD is r, then the angle theta in radians will be equal to the arc length S divided by the radius r. As you can also see here, because the arc length S and the radius r have the same units, the radian is a dimensionless unit. It is simply used as a placeholder to indicate that the rotational motion is considered in the framework of the metric system. For one full revolution, the angle theta will be equal to the circumference of the CD, so that is 2 times pi times r, divided by the radius r, or one full revolution encloses an angle of 2 times pi radians. So we know that one full revolution also has 360 degrees. So therefore 2 pi radians is equal to 360 degrees. Let's apply the definition for the angle of rotation or the angular displacement in a simple example. Synchronous satellites are put into an orbit whose radius is 4.23 times 10 to the 7th meters. If the angular separation of the two satellites is 2 degrees, find the arc length that separates them. So the first task is to convert the angle from degrees to radians. We know that 2 pi radians are equal to 360 degrees. So therefore, if I multiply the angle 2 degrees by 2 pi radians and divide by 360 degrees, that's going to cancel the units of degrees. It's going to give me the answer in radians, and that is 0.0349 radians. From the definition of the angle in radians, theta, I can rearrange the terms and find that the arc length s is equal to the radius of the orbit times the angle between the two satellites. So that is 4.23 times 10 to the 7th meters times 0.0349 radians, or that is equal to 1.48 times 10 to the 6th meters. Remember that radians are dimensionless units, and so the arc length is supposed to be in units of meters, and radians are not affecting that because, again, that is a dimensionless unit. So I defined angular displacement delta theta. The question is, how fast will a point P on the edge of this CD get from this initial position to this final position on the CD? How fast will this point P travel through that angular displacement? To be able to answer this question, we need to introduce another kinematic quantity associated with rotational motion. That kinematic quantity is the average angular velocity. The average angular velocity is described as, or defined as, the angular displacement divided by the elapsed time. In other words, the average angular velocity omega is equal to the final angular position minus the initial angular position, so that is the angular displacement delta theta, divided by the timestamp at each position, the difference between the timestamps at each position, so that is the elapsed time. In the metric system, the units for angular displacement are radians, the units for time are seconds, so therefore the average angular velocity is measured in radians per second. Here is a simple example that combines the definitions of angular displacement and average angular velocity. We have a gymnast on a high bar who swings through 2 revolutions in a time of 1.9 seconds. Find the average angular velocity of the gymnast. So the angular displacement is given in revolutions, and therefore it needs to be converted into radians. We know that 1 revolution around the circle has an angle of 2 pi radians. So therefore, if I multiply 2 revolutions by 2 pi radians and divide by 1 revolution, the units of revolutions cancel out, and then as a result I get 12.6 radians. The minus sign is added here because the rotation is in clockwise direction around the bar, and if you remember, the rotation in clockwise direction causes negative angular displacement, and rotation in clockwise direction causes positive angular displacement. So the angular displacement here is negative. That's why we have the minus sign. So the angular displacement in radians is negative 12.6 radians. Then I apply the definition of angular velocity. That is the angular displacement divided by the elapsed time. And as a result, the angular velocity is negative 6.63 radians per second. Now consider a disk that rotates in counterclockwise direction. And let's look at a point P on the edge of the disk. So the point P initially is at some initial position, I, and has angular velocity omega 1. And at the later moment of time, the point P is somewhere here. Let's call that the final position. And now the angular velocity is different. Let's call it omega 2. The interval of time between the two positions of point P, let's call delta t. Well, since there is a change in angular velocity, whether that is increase or decrease, that means that there must be acceleration in the motion of this point, and in general, the motion of the entire disk. So, changing angular velocity means that an angular acceleration is occurring. The angular acceleration is defined as the change in angular velocity divided by elapsed time. The angular acceleration alpha is equal to the change in angular velocity omega minus omega 0 divided by the elapsed time t minus t0, or in other words, that is delta omega divided by delta t. The units for angular acceleration are the units for angular velocity divided by the unit of time, so that is radians per second squared. Here's an example that illustrates the concept of angular acceleration. As seen from the front of the engine, the fan blades of a jet engine rotate with an angular speed of negative 110 radians per second. As the plane takes off, the angular velocity of the blades reaches negative 330 radians per second in a time of 14 seconds. Find the angular acceleration, assuming it to be constant. So before I talk about the calculation of the angular acceleration, I'd like to point your attention to the signs of the angular velocity. The negative sign implies that the rotation is in clockwise direction, as shown in the drawing here. Okay, so the definition of angular acceleration was change in angular velocity divided by elapsed time. So the change in angular velocity is the final angular velocity, negative 330 radians per second, minus the initial angular velocity, which is negative 110 radians per second, divided by 14 seconds. And the result is negative 16 radians per second squared. The minus sign here in front of the acceleration value indicates that the blades here are spinning in clockwise direction and also speeding up. As you have seen already, there is a definite similarity between the definitions of angular displacement, angular velocity, and angular acceleration, and the definitions of linear displacement, linear velocity, and linear acceleration. Therefore, we can expect that the kinematic equations of motion that we discussed before will also apply with modifications for the symbols for rotational motion. So, as a quick review, here are the kinematic equations that we've dealt with before. The kinematic variables are the displacement x, the acceleration a, final velocity v, initial velocity v0, and elapsed time t. So I can essentially rewrite those kinematic equations by replacing the corresponding quantities with the rotational counterparts. So for angular velocity, the final angular velocity is equal to initial angular velocity plus angular acceleration times time. The angular displacement is 1/2 initial plus final angular velocity times the time. Angular velocity to the second power is equal to angular velocity initial to the second power plus 2 times angular acceleration times angular displacement. And finally, the angular displacement is calculated as the initial angular velocity times time plus 1/2 the angular acceleration times time to the second power. As you can see, these kinematic equations for rotational motion with constant angular acceleration have the exact same form as the kinematics counterparts here. Just the quantities are replaced with their rotational counterparts. That means that dealing with problems about rotational kinematics essentially is identical to dealing with problems on linear kinematics, with the caveat that now we're talking about rotation and not linear motion. We're going around a fixed axis, and therefore everything is measured in angular measures. Here is a table that matches the rotational motion variables with the linear motion variables. And here is another table which matches the linear kinematic motion equations with the rotational kinematic motion equations. So what is the reasoning strategy when you're dealing with rotational kinematic problems? You will make a drawing first, and you will indicate the axis of rotation and all important points or features that relate to the problem at hand. Decide which direction is to be called the positive and the negative. In this textbook, we use counterclockwise direction of rotation as the positive direction, and clockwise direction of rotation as the negative direction. So then you write down the values that are given for any of the 5 kinematic variables, and you will also include the units. Then verify that the information contains values for at least 3 of the 5 kinematic variables, and then select the appropriate equation that you can use to solve the problem. When the motion is divided into segments, remember that the final angular velocity of one segment is the initial velocity for the next. Keep in mind that there may be 2 possible answers to a kinematics problem. For example, the equations that have the angular velocity to the second power or the time to the second power. Those may result in solving quadratic equations which have 2 solutions. And so let's look at the following example. The blades of this blender are whirling with an angular velocity of 375 radians per second when the puree button is pushed. When the blend button is pushed, the blades accelerate and reach a greater angular velocity after the blades have rotated through an angular displacement of 44 radians. The angular acceleration has a constant value of 1740 radians per second squared. Find the final angular velocity of the blades. So in this table here, I have indicated the 5 kinematic variables for rotational motion, and I've written down the values of the 3 that I know. So the angular displacement theta is 44 radians. The angular acceleration alpha is 1740 radians per second squared. The initial angular velocity omega 0 is 375 radians per second, and I want to find the final angular velocity. I do not know how long it took for the angular velocity to change from the initial value to the final value. So therefore, looking at the kinematic equations for rotational motion, this equation here has all these known variables and the unknown variable. So replacing the known values in this expression gives me the final angular velocity is 542 radians per second. It turns out that there's a relationship between rotational variables and linear variables. There's a relationship between angular velocity and linear velocity of motion, and there is a relationship between angular acceleration and linear acceleration. So let's see how we can find those and define those relationships. Here we have 5 skaters that are forming a line and are rotating around a circle, with this skater right here being in the center, while trying to maintain this line straight. So all of them rotate around the circle with a center at this skater, and at the same time the line must remain straight. So each skater will be moving with different velocity with respect to the axis of rotation, because that is the only possible way for the line of skaters to remain straight. The skater that is furthest from the center of rotation will have to move the fastest, because he will have to go the longest distance around the center, and the skater that is closest will be moving with the smallest velocity, because he has to go a smaller or very small distance around the center. So every skater will be moving with different velocity, and these velocities must be matched exactly so that this line remains straight. At the same time, the skaters are also trying to skate faster and faster as they go around the circle. So that means that their velocities increase all the time as they are going around the circle. So, since this is a circular motion, there has to be a relationship between the linear velocity for each skater and the angular velocity of rotation around this axis of rotation for each skater. Now let's look at only one skater. The skater that is in the center of the circle, and then the second skater is the skater that goes around the circle. So the skater that goes around the circle travels an arc length s between 2 points during the rotation. The radius of the circle is the distance between the two skaters, r, and the angle that this arc defines between the two positions of the skater is theta. So we know from linear kinematics that the speed of rotation of this skater here would be equal to the path length of the path traveled divided by the time. So s divided by t. S divided by t. Okay, but we also know from the definition of angular displacement that the angle theta is equal to s divided by r. So therefore, I can replace r times theta for s in this formula right here. So s becomes r times theta, and then we divide that by the time t. Now I can group theta and t in a ratio like so, and remember that that is the definition of angular velocity. So ultimately, it becomes, we get the result that the tangential velocity of the skater is equal to the angular velocity of rotation times the radius of the trajectory of this skater. And here we have the tangential velocity of the skater at the two different points. So one more time, the relationship between the linear velocity of the skater and the angular velocity of rotation is given by this formula here. The linear velocity is equal to the radius of the trajectory of rotation times the angular velocity. As I mentioned, this line of skaters has to remain straight, while at the same time every skater accelerates. So they're trying to spin faster and faster and faster and faster around this axis of rotation here at this skater. That means that each of those skaters is also accelerating. We know that the linear acceleration is calculated as the change in linear velocity divided by the elapsed time. However, I can replace those two linear velocities with their equals from the relationship with the angular velocities. And so I get r omega minus r omega 0 divided by t. And I can rearrange the terms again to get r times omega minus omega 0 divided by t. Remember now that this ratio here is defined as the angular acceleration. And so if I substitute the angular acceleration here, I have a relationship now between the acceleration of the skater, or each skater, and the angular acceleration of the rotational motion. The acceleration of each skater that increases their linear velocity is known as the tangential acceleration. And so the tangential acceleration is equal to the product of the radius of the circular trajectory and the angular acceleration of rotation. So if this is the linear velocity of the skater at this point, at this later point the linear velocity is larger, and so for that to happen there has to be a linear acceleration present, and the linear acceleration or tangential acceleration is directed as so as well. It is called tangential acceleration because it is tangent to the circular trajectory of this skater. So here I want to emphasize that this is tangential acceleration, and there is also centripetal acceleration acting on each skater and towards the center of the circular trajectory. This acceleration we are not discussing right here. This is the tangential acceleration. Now let's look at one example that uses the concept of the relationship between angular and linear quantities. A helicopter blade has an angular speed of 6.5 revolutions per second and an angular acceleration of 1.3 revolutions per second squared. For point 1 on the blade, right here, find the magnitude of the tangential speed and the tangential acceleration. So the angular speed is given in units of revolutions per second, which means that this must be converted into radians per second. So the conversion is 6.5 revolutions per second times 2 pi radians divided by 1 revolution. The units of revolutions cancel out, and then we have 6.5 times 2 times pi, that is equal to 40.8 radians per second. So to find the linear or tangential speed of rotation, I multiply the radius of this of rotation of this point here by the angular velocity. So that is 3 meters times 40.8 radians per second, or that is 122 meters per second. To find the tangential acceleration, I now notice that the angular acceleration is in units of revolutions per second squared, which means that I must convert the units here to be radians. So the conversion happens by multiplying 1.3 revolutions per second squared by 2 pi radians per revolution. The units of revolutions cancel out here as well. And then I have 1.3 times 2 times pi, that's equal to 8.17 radians per second squared. Then to find the tangential acceleration, I multiply the angular acceleration by the radius of rotation of this point. So that is 3 meters times 8.17 radians per second squared, and that gives us 24.5 meters per second squared. Now let's talk about the centripetal acceleration. So we know that for an object that undergoes circular motion like this, there has to be a centripetal acceleration directed towards the center of this circular trajectory. And we know that the centripetal acceleration is calculated as the product of the tangential velocity to the second power not the product, but the ratio of the tangential velocity to the second power divided by the radius of the trajectory. But we know now that the tangential velocity is equal to the product of the radius of the trajectory and the angular velocity. So if I substitute that here for Vt, I get r omega to the second power divided by r, or I get that the centripetal acceleration is equal to the radius of the circular trajectory times the angular velocity to the second power. So I have a relationship between the centripetal acceleration and the angular velocity of rotation. And finally, for an object that undergoes circular motion like that, here is the full picture of the acceleration that acts on this object. We have the tangential portion and we have the centripetal portion. And those two vectors add up to give us the total acceleration of this object, and that is in that direction. Now let's look at one example which uses the concept of tangential and centripetal acceleration. We have a discus thrower. Starting from rest, the thrower accelerates the discus to a final angular speed of 15 radians per second in a time of 0.270 seconds before releasing the disc. During the acceleration, the discus moves in a circular arc of radius 0.810 meters. Find the magnitude of the total acceleration A of this discus. So here I'm going to use the relationship between the centripetal acceleration and the angular velocity of rotation, which states that the centripetal acceleration is equal to the radius times the angular velocity to the second power. So that is 0.81 meters times 15 radians per second to the second power. That is 182 meters per second squared. For the tangential acceleration, we have that is equal to the radius times the angular acceleration. And here I will replace the angular acceleration with the change in angular velocity divided by time. So that is equal to the tangential acceleration is equal to the radius times the change in angular velocity divided by the elapsed time. So that is 0.81 meters times 15 radians per second divided by 0.27 seconds. That gives us 45 meters per second squared. The total acceleration magnitude is calculated as the square root of the sum of the squares of the tangential and centripetal acceleration. Notice here that the tangential and centripetal accelerations are just the components of the total acceleration. So I can apply the Pythagorean theorem to calculate the magnitude of the total acceleration. Substituted the values for the centripetal and tangential accelerations gives us 187 meters per second squared. Finally, the angular velocity is a vector quantity. However, the way that this vector quantity is shown in drawings is different than the way that tangential velocity is shown in drawings. Why is that? Well, because if you look at the point P right here, its linear velocity is tangent to the edge of this disk as the point rotates around the axis of rotation. The linear velocity is always tangent to the disk. Okay? So the magnitude, let's say that the rotation is with constant acceleration, so the magnitude of this velocity doesn't change. However, the direction changes all the time. But for the angular velocity, if the rotation happens with no acceleration, the angular velocity doesn't change. So therefore, it cannot be drawn as a tangent to the disk. It has to be drawn in a different way. And so what makes sense is to have the angular velocity along the axis of rotation with direction determined by the right-hand rule. So the right-hand rule states that if you grasp the axis of rotation with your right hand so that your fingers circle the axis in the same sense as the rotation, your extended thumb points along the axis in the direction of the angular velocity. So in the first example here, the rotation is in counterclockwise direction. So if you place your right hand in such a way that your fingers point in the direction of rotation, then your thumb is going to point in the direction of the angular velocity vector. In the second example, the rotation is in clockwise direction. So if you place the fingers of your right hand in the direction of rotation, your extended thumb will point in the direction of the angular velocity vector. And the angular velocity vector lies on the axis of rotation. So this is the right hand rule, and it's very useful to determine the direction of angular velocity. The direction of the angular acceleration can be guessed based on the change of the angular velocity vector. If this vector increases with time, that means that the angular acceleration vector points in the same direction. If this vector decreases with time, that means that the angular acceleration vector points in opposite direction. These are the basic rules of determining the direction of the angular velocity and angular acceleration. And with this, I conclude the lecture on kinematics of rotational motion.